Okay, so in this video, we're going to talk about the modular exponentiation. And this is a way to do the control U operations in the order finding circuit to be efficient. Okay, so let me remind you about the order finding circuit. So we have the stop registers, which have the Hadamard gates. And let's say there are T bits over here, and then there are the control U operations. So this is my get1 vector, and this is my control U operations that go like this. So this is U 2 to the power 0, and then we have this one that is control U 2 to the power T minus 1. And our goal is to try and optimally or efficiently implement these control U operations. Okay, so right over here, we have the uniform superposition, and one of the vectors can be J, and which has the bit representation J1, J2, and JT. And let me remind you what the U operation, U acting on Y is equal to XY mod N. And well, U square acting on Y will be equal to X to the power 2Y mod N. In general, if I have U to the power K, then it will be X to the power K mod N. Okay. Now, what does the control U operation really do? So we have, let's say we start with J tensor some Y. And this whole control U to the J operation does the following. This is the control bit, and then you have U. This is the bits are, I'm going to order them from J1, J2, and JT, right? So the control U operation just applies the U gate depending on the bit. So J1 will be raised to 2 to the power T minus 1 multiplied by U J2 to the power 2 to the power T minus 2, and then so on multiplied by U J T 2 to the power 0, and then Y. Right? So I'm going to use this definition of U to the power K. So this is going to be J, and then we'll have X to the power J1 2 to the power T minus 1 into X to the power J2 2 to the power T minus 2, and so on till X to the power JT Y mod N, right? This is after the application of control, but this is just X to the power J because this is the binary representation of J. So this whole control J, control U to the J operation is just goes to this X to the J Y mod N. And this is why it's called the modular exponential. So all we need to do is to implement this X to the J mod N, because recall that this is the bottom register is just in this one state. So this is going to be J X to the J mod N. So therefore, we need to be able to implement, sorry, I need to clear this page. So I need to be able to implement x to the j mod n for an arbitrary j, where, right? So the question is, can we do this implement efficiently? Right now, let's assume that capital N is equal to 2 to the L, and this T that we are choosing over here is order L. Actually, it's going to be, T is going to be exactly 2L plus 1 plus log of 2 plus 1 over 2 epsilon. But right now we just assume that it's of order L. Now, how do I implement this x to the j, which is called the modular? This is called the modular exponentiation. So I know that I can implement x, then x square mod n. It is just squaring this. Then I can also implement the square of this, which is x power 4 mod n, and so on. And I can go right up till x to the power 2 raised to t minus 1 mod n. Right? So, and it turns out that each of these squaring operations require only order of L square basic operations. So there are roughly T of them. So T of them, and then each of them require order L square basic operations. Right? But we need to be able to compute the intermediate. So I need to be able to compute x to the j mod n for j not equal to power of 2, let's say, right? Then how do we do that? Well, I use the fact that x to the j mod n, I can write j in the binary representation as j1, j2, jn. Then this is due to the fact that I can write this as x to the j1 into 2 to the power t minus 1 mod n into, so this is a fact, so this is j2 into 2 to the t minus 2 mod n, and so on, into x to the jt into 2 to the 0 mod n. And each of these multiplications inside are some power of 2, which we can compute in order L square operations. And then there are T of them. So the total runtime of this is order of L cube operations. So modular exponentiation takes L cube, order of L cube operation, where 2 to the power L is our n, right? Capital N. So this is a trick used to simplify and efficiently implement the control U operations. Basically, the whole um, point is that the control U operations are equivalent to the modular exponentiation, and the modular exponentiation can be implemented efficiently using this fact in order of L cube operations.